So on this handout here, what I've got is I've just got it set up where we can do a lot of these limit definitions for several different functions. The first one is just the constant function. C is a constant. C is here is, you can let it be C there. C is any constant you want. 5, 10, 15, whatever you want. If you use the limit definition of derivative, which, you know, there's our Leibniz notation, and that's kind of why we went over the Leibniz notation just now. This is saying, right, what's the derivative then if you've got, you know, your function is a constant, say 2 or 3? Well, it turns out it doesn't matter, because if you use the limit definition, which, you know, I'm talking about f prime equals the limit h approaches 0, f of x plus h minus f of x over h. I'm using that here, but since my function is a constant, what is f of x plus h when the function is c? Well, f of x plus h is c, right? There's nothing to plug in x plus h into. It's always constant. F of x is also c, isn't it? Because there's nothing to plug in. C minus c is on top over h. Well, what is c minus c over h? 0 over h, which is 0. What's the limit as h approaches 0? There. Okay. All right. So what's the limit as h approaches 0 of 0? Be 0, wouldn't it? Okay. Therefore, the derivative of a constant is always 0. Yeah, if you want the derivative, this is what this is saying. If I've got f of x equals 5, the derivative of a constant is always 0. So the derivative would be 0. If, see if I can do this, if it was, down there, 6, what's the derivative? F of x was 6. Derivative is 0. If it was 612, f of x is 612, the derivative is still 0. That's what that's saying. Anytime you just have a number, the derivative is 0. Okay. All right. Now, number 2, line 2. Here. d dx of x. That's saying my function is x. All right. So I put this all together so it'll go pretty quickly here, hopefully. The limit as h approaches 0, then I'm going back to my limit definition. Right here, this is all what it gets back to, right? If I do that when the function is x, that's what this is saying. This function is x. Isn't this the limit that I'm doing, x plus h minus x? Would y'all believe that? Over h? Because I'm just plugging in x plus h for x. And so it's x plus h minus x. Well, what happens? Well, you get the limit. Isn't that just h over h? Which is the limit of 1, h approaches 0. What's the limit as h approaches 0 of 1? It's 1. Okay? Number 3, d dx of x squared. That's saying your function is x squared. What's the derivative? Well, the derivative of x squared is going to be x plus h squared, because I'm plugging in x plus h for x there. So you get x plus h squared. Minus x squared over h. Well, if you FOIL that out, don't you get x squared plus 2xh plus h squared right here? What happens? The x squareds cancel. I get 2xh plus h squared over h. Factor out an h there. 2x plus h over h. GH's cancel. H is going to 0, so isn't that just 2x? Derivative is 2x. X cubed. And this is why I really did this, so we can really jump to the point here. If you do x cubed the same way, you get x plus h cubed minus x cubed. Well, if you do all that foiled out, quote unquote, here's what you get. X plus h cubed turns into this. With me? Okay, what happens? Well, the minus x cubes cancel, so we have 3x squared h, 3x squared, H factors out again, so I have 3x squared plus 3xh plus h squared. Should have gave myself a little more room there. Over h. The h's cancel. What's the limit as h goes to 0 of that? 3x squared. One more. All right, so now we're up to x to the fourth. X plus h to the fourth minus x to the fourth. Wouldn't that be plugging that into the limit definition? Okay. Well, if you do x plus h to the fourth, here's what you get. A long string. So you wouldn't have to write all that out. That's what you get. Guess what? The x to the fourth cancel. We have 4x cubed h. There's an h common factor. It'd be h times 4x cubed. 6h squared h. So h comes out. 4x h squared. Almost had enough room there. And h to the third. Okay? On top, over h. The h's cancel. H is going to 0, so that goes to 0, that goes to 0, that goes. It's 4x cubed. Do we see a pattern? Is everybody okay with that? All from the limit definition. But do we see a pattern? And if you know, don't spoil the fun. Okay? All right. So here, well, let's start with x squared. I started with x squared. The derivative then is 2x. If I started with the function as x cubed, the derivative is 3x squared. If I start with x to the fourth, the derivative is 4x cubed. For those of you who have not seen this before, do you see a pattern? What's the pattern? What happened to the power? It goes down by 1, doesn't it? I started with x squared, it came down to 1. I started with x cubed, it came down for the derivative to be x squared. I started with x to the fourth, it came down 1, subtracted 1 to be x cubed. Where did this number come from? The one in front. 4, 3, 2. It's what the power was, yeah. So what I basically did is I brought down the power for x squared. I brought down the power, and then I subtracted 1 from the power. It works on all those for the derivative, doesn't it? Now, does it work for the x? Well, that's x to the first. So if I start with x to the first, bring down the power, and subtract 1 from that power, what do you get? X to the 0, which is, what is x to the 0 power? It's 1, which is exactly what I got. Huh. Okay. So here's the deal. This is called the power rule. The derivative power rule. If you want the derivative with respect to x of x to a power, and it works for any variable to any power, what do? Well, you bring down the power, and I do it in general, x to the n. You bring down the power, so that would be n in this case, right? And then the x to the new power would be 1 less power. Pretty nice, huh? Okay, how about we use the power rule on these? I can find them. All right, f of x equals, let's just start x to the 9th. What's the derivative? Nine x to the 8th. Instead of having to do the limit as h approaches 0, I know you're sad to see that go, but it's going to be 9x to the 8th. If we did that all out, do the same thing, do the x to the 9th power, which you'd want to get into binomial theorem and all that if you did that, but it's going to be 9x to the 8th for the derivative. All right, what if y equals x to the minus 3. Now, you got to be careful on this one. The derivative, y prime, would equal negative 3, right, x to what? Negative 2, negative 4. I got two answers here. It's negative 3 minus 1, isn't it? I subtract 1. That's a negative 4. Yes, got to be careful on those. All right, what about g of t equals the square root of t? What's g prime of t? Well, think of square root of t as t to the 1/2. The square root is 1/2 power. The cube root is 1/3 power. So change that over to the 1/2 power, the square root. All right, so that's going to be, bring down the powers, 1/2. T, and then I do 1/2 power minus 1. So what is that going to be? It's 1/2 t to the minus 1/2, isn't it? Now, what about f of x equals 7x to the 5th? Well, I do a little explanation here. If you've got a constant in front, which that's what I've got, a constant in front, that constant really just kind of comes out at the end, and so you wind up with the very same thing we had before, this limit as h approaches 0. Moral of the story is to do the derivative here, you wind up with 7 times, and then just do the derivative of that. 5x to the 4th, which is 35x to the 4th. Yeah, you wind up just multiplying the constant by your derivative, because that right there is the derivative. So you just do the constant times your derivative. Okay? All right. Now, the second page, real quick, is really just FYI there. Here's some useful derivative rules. Yeah, if you have two things added together, f plus g, it turns out then the derivative is just the derivative of f plus the derivative of g. And there's the step-by-step. You can do it with the limit rule, the limit definition rule. Start with f plus g, and you wind up with f prime plus g prime. Same thing can be done with f prime minus f minus g. It turns out the derivative is just f prime minus g prime, and there's all the step-by-step, and you wind up with, through the limit definition, y prime is f prime minus g prime. What does that mean? I just thought of a couple more I should have done a while ago. But anyway, what that means is if I have h of x equals x squared plus 2x to the 3rd plus 5x to the 4th. Let's make that. Look at that. Get out of here. Minus. Okay. Minus 5x to the 4th. What does that do? Get over there. Okay. That means, by all this, the h prime is, because aren't these added and subtracted together? Those rules tell me I can just do the derivative of this, which is 2x to the 1st, right? Plus the derivative of this, which is 2 times 3, which would be 6, x squared, minus the derivative of this, which is 20x to the 3rd. With me on that? Since these are added and subtracted, you can do that all day. Now, be careful. That's adding and subtracting. You can do that all day long. You can't do it with multiplication. You can't do it with division. We've got to talk about those rules next time. But it only works for adding and subtracting functions like this. The other ones I was wanting to mention, oh, yeah. What's the derivative there? What's the derivative? So these are subtracted, so I can just do the derivative of this, derivative of 3x, which bring down the power, which is 1, so that'd be 3, and then subtract 1 from the power, it's x to the 0, so yeah, it's just 3. And then what's the derivative of, what's the derivative of, isn't the derivative of that 0? Derivative of the constant is 0. So that's just 3, right? But one more I was going to mention. F of x equals, what would I do with 1 over x to the 7th? One over x to the 7th. So next to the 6th? No, the thing you want to do here is change that to be in the numerator. Flip it over. What would it be in the top? X to the negative 7. So I'm going to bring down the negative 7 and make it x to the negative 8, right? Because the derivative, you subtract 1 from the original power. So the derivative is negative 7. I wanted to mention that one. Yeah, if you've got one,